Okay, the last part of fatty acid catabolism that we're going to talk about is a process called beta oxidation. Beta oxidation occurs again in the mitochondria, and that's why we had to spend all that time to get our carbon chain into the mitochondria. Beta oxidation is a four-step process, basically, that is going to generate those reduced cofactors that we talked about in the first video, plus acetyl-CoA. I'm going to do this example on, again, a pretty short acyl-CoA molecule. Whoop, SCOA, that we've gotten in the mitochondria. Okay, it's helpful when you think of beta oxidation to start labeling the alpha and beta carbons. That's where the beta comes from. Here's our functional group, the carbonyl. And so the carbon directly attached to that functional group is our alpha carbon. The next carbon is the beta carbon. In essence, what we're going to do is we're going to oxidize this area around the alpha and beta carbon to generate a carbonyl group on the beta so that we can chop away an acetyl-CoA and leave us with a shorter acyl-CoA, shorter by 2 carbons. The first step in this process is a oxidation process that generates a double bond between the alpha and the beta carbon. Now, this is catalyzed by a dehydrogenase enzyme, and since we're oxidizing this carbon-carbon bond, we are going to generate a reduced cofactor, and this is where the FADH2 comes from in beta oxidation. Okay, the next step hydrates that double bond. Hopefully you remember from Orgo-1 or Orgo-2 these hydration reactions. It's an addition reaction to an alkene. So we're adding an H and an OH to this double bond, and this is catalyzed by hydratase. So we can add 2 things across that double bond. We're not going to do it in a Markovnikov or an anti-Markovnikov fashion because these 2 carbons are equally rich, but it's the beta carbon that always gets the alcohol group. Okay, that's supposed to be a T, hydratase. Okay, the next thing we're going to do is we're going to oxidize that alcohol group that we've just added to our carbon chain from an alcohol to a carbonyl. And this is done again by another dehydrogenase enzyme. And since we're oxidizing this alcohol, we can reduce something else. And in this case, we have enough reducing power to put a hydrogen onto NAD to make NADH. Okay, now look what we've done here, right? We've taken this carbon chain and really we've focused on this beta carbon, putting a carbonyl group on it. And so now hopefully you can see we've got sort of an acetyl-CoA right here, right? 2 carbons. And then, so if we, if we sort of cut this right here with what's called a thiotransferase, you don't have to know that, we can generate a new acyl-CoA by adding our coenzyme in here, plus our molecule of acetyl-CoA. Okay. So I'm going to label this acyl-CoA as a -2. Okay, because it's shorter by 2 carbons than what we had originally, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay, where'd those 2 carbons go? Well, they made our 2-carbon acetyl-CoA, which can go into the Krebs cycle to generate, for every acetyl-CoA that we put in the Krebs cycle, we get 2 carbon dioxides, right? We get 3 NADHs. We get 1 FADH2 and our GTP. Okay, so if we start to think about accounting, we've got some reduced cofactors that come from every round of beta oxidation that we do. And then for a particular acyl-CoA, we got the potential to make a bunch of these acetyl-CoAs, which we can throw into the Krebs cycle to give us a bunch more reduced cofactors. So in class, we're going to go through this process of accounting and try to think about how many ATP equivalents can we get from, an 18 carbon fatty acid or 22 or whatever. And we're going to have to think about, how much it costs to charge it, how many rounds of beta oxidation are necessary to chop a particular carbon chain into 2 carbon pieces, and then how many how many acetyl-CoAs are we making from that?